he's working at BHU since many years, guiding students and so on. And let's hear from Professor Devendra Mishra, please.
Thank you, Dr. Mehta. So, good afternoon to all of you. My talk is based on the quantum enhanced super sensitivity of squeezing assisted interferometer using two-channel detection.
Could you please make your slide full screen?
This is full screen or not?
No, no, it's not. Oh, you are opening in some Google Drive or something. Please download and open it again.
Okay. Now this is visible?
Yes.
Yeah,
yes.
thank you.
But still it is not full screen. Please make it Control L. That would make it full screen.
Now?
No. If you go to View and full screen, I think that will work.
Yes. So hope that now it is working.
No, it's not visible. We can see your window where you have all the files. Please unshare and share again in Zoom. Yes, perfect. Now it's fine.
Okay, thank you.
Yeah.
So I am trying to discuss about the enhancement in sensitivity of interferometers by using two-channel detection as well as squeezing. Okay. The outlines of my talk is we will first discuss about the introductions of quantum optics. For example, non-classical states, beam splitter, etc. Second one is the detection schemes. Third one is classical and quantum parameter estimation, in which I will try to discuss about the basics of Fisher information and Kramer-Rao bound and its quantum analog, quantum Fisher information, as well as quantum Kramer-Rao bound. And I will discuss about some basic results which we have done here. In a single mode pure state, we can write this as get psi as a superposition in terms of Fock states and infinite dimensional separable Hilbert space with an infinite countable orthonormal basis in terms of number states. Fock basis comes with canonical adjoint operators A and A dagger, referred to as annihilation and creation operators, respectively, are photon subtraction as well as photon addition operators in the context of optical quantum information processing, and we can define mathematically the creation and annihilation operators in terms of these relations. Coherent state is an eigenstate of annihilation operator, and this can be represented in written in terms of Fock state by this equation. And we can define also canonical position like and momentum like operators in terms of P and Q. We can define we are well aware about the Wigner function, which is a non-singular distribution for all states. That is an example of quasi-probability distribution function. This contrasts with classical phase space probability distribution. Hudson theorem says that a pure quantum state is non-Gaussian if and only if its Wigner function has negative value. There are other witnesses for non-Gaussianity as well as Gaussianity. Wigner function can also be written in terms of parity operator, and we can define the P function in terms of a diagonal coherent state representation of a state written in terms of density operator rho equal to integral of integral in terms of this relation. And Husimi-Kano Q function is a smoother version of Wigner as well as Glauber-Sudarshan P function. Okay, there exists a continuum of equivalent phase space distributions representing the same operator in phase space. This can be written in terms of a general operator T. In this way, the phase space representation with parameter S of an operator is defined as W, which is a function of alpha S equal to trace of T and O. There are three most prominent representations. For example, Wigner function, Glauber-Sudarshan P function, and Husimi Q function. And we can define the Wigner function, P function, and Q function in terms of a generalized function W alpha 1. So Gaussian states and processes in phase space are well known, and they are of very high interest. Circles are normalized Gaussian probability distributions. The coherent states viewed, we can see here, the coherent states viewed from the top, and ellipse represents the squeezed Gaussian probability distribution function. And this is the in red color. We can see that this is a squeezed. This is representing squeezed state. A vertical blue line and horizontal green line correspond to the position and momentum eigenstates respectively. We can define also the displacement operator in terms of exponential of alpha A dagger minus alpha star A. Further, we can define squeezing operator. Yes, xi equal to exponential of half xi A square minus xi star A dagger square. In classical case, we have a beam splitter which can behave as a single input and two output. But in quantum mechanical or quantum version, we cannot skip the second input in the case of beam splitter. So no input here. This is wrong. And in quantum case, we need to consider vacuum also if we are considering only one input. So the input output mode transformations in the case of beam splitter, which is a 4-port device having two input and two outputs. Inputs are represented in terms of annihilation operators A2 and A1, and outputs are represented in terms of A3 and A4. Then we can find out the output mode transformation in terms of input modes of the beam splitter by using this relation, where T and R are the transmission and reflection coefficients of the beam splitter. Using this, we can find out the linear interferometers. A passive linear transformation over M modes are defined as the unitary transformation U, which act unitarily on the creation operators of modes A1 dagger, A2 dagger, and so on up to AM dagger, as well as on the annihilation operators A1, A2, AM, and so on. Any such transformation U is associated with M cross M, a unitary matrix which transforms the creation operators in this way, as well as the annihilation operators of the modes are transformed by using this relation. Using beam splitter and other things, we can construct a Magenta interferometer, which can be drawn in this far. Here, the electromagnetic fields propagating through this device are simply labeled by their corresponding annihilation operators A0 and B0. The initial input fields A0 and B0 are injected into a 50-50 beam splitter, resulting the output probe fields A and B. So a relative phase difference acquired by the probe fields is described by the transformation B, transforming to B e power I5. After the phase shift operation, the fields are recombined using a second 50-50 beam splitter, resulting in the final output fields AF and BF, which are subjected to a measurement in order to determine the value of phase shift. This is a building block of a Magenta interferometer. There are 3 steps of parameter estimation in a Magenta interferometry. First one is the probe preparation. An initial field is injected into a beam splitter, resulting in output modes A and B. Second step is probe modifications. These optical modes require a phase difference phi equal to phi A minus phi B, resulting from their corresponding path difference. Third and most important step in this setup is probe readout. We recombine these modes with a second beam splitter and perform a photon counting measurement on the output. So in Magenta interferometry, we have 3 steps. First one is input state mixing. Second one is state evolution inside the Magenta interferometer, and final stage is measurement. So if we, in a measurement scheme, we define an observable O dependent on the parameter phi, external phase phi. The average of the operator is expectation value of operator O, which is dependent on the parameter phi, where state psi is the state of the system. For a delta phi variation in the phase phi, we have expectation value of operator O dependent on phi as well as delta phi is can be written approximately in terms of this relation. The phase sensitivity of the state of art of interferometers is limited by quantum fluctuations. First one is short noise limit. Short noise limit is equal to 1 upon square root of n, where n being the number of quanta used for the measurement. The sensitivity can be improved by increasing the number of photons. Now question is, can we surpass this limit? Answer is yes. Now let us see how. The problem of parameter estimation in quantum metrology can be divided in 3 steps, as we have discussed. In the first step, we prepare a quantum state get psi that will serve as the probe. Next, we will consider this probe state to interact with a system of interest such that get psi evolves to a state get psi dependent on phi, which which is a parameter phi that we would like to estimate. In the final step, we are considering an observable O of the modified probe state psi phi in order to gain information, extract the information about the value of parameter phi. The error in this measurement, measured quantity, actually we have to say this is the estimated quantity, is related to the error in the measured operator O by the following formula. This is from error analysis. Delta square phi is equal to delta operator O and divided by this relation. This is the ratio of the signal noise to how the signal changes with respect to phi. The quantum Fisher information determines the theoretical lower bound to the error, and it is obtained by optimizing over all conceivable measurements that can be performed on ket psi in order to gain information about the value of parameter phi. In other words, the quantum Fisher information is independent of the measurement technique. Quantum Fisher information can be written in terms of this relation, where the primes denote the derivatives with respect to phi parameter. This is used to bound the phase error delta phi, and the ultimate bound for this in this calculation is in terms of quantum Kramer-Rao bound, which is expressed in terms of delta square phi, which is greater than or equal to 1 upon f, where f is quantum Fisher information in the case of quantum case. In estimating phi from the measurement signal, expectation value of n d, we must propagate the error from the signal to the estimated value via the following formula from the error analysis, as we have discussed. Optimal phase sensitivity of the classical Magenta interferometer. Here, classical means we are considering classical states. Coherent the setup is coherent state and vacuum. Namely, this is the short noise limit, which is equal to 1 upon square root of n bar. In order to surpass this short noise limit using Magenta interferometer, we have to utilize states of light for which photons possess non-classical correlation. That is, they are no longer randomly distributed as in the case of laser field. With squeezed states, we can reach up to Heisenberg limit, which is equal to 1 upon n bar. Caves originally proposed to utilize an intensity difference measurement, and for which most of the energy come from the initial coherent field injected into the Magenta interferometer. This is the most accessible quantum enhanced interferometry protocol for practical macroscopic applications. And the successful detection of gravitational waves in LIGO experiment is a very recent example for the success of such a setup. Now, question is that, is there any state from which we can reach up to the Heisenberg limit? Answer is yes. The state is noon state proposed by Jonathan Dowling. Noon state is defined in terms of 1 upon square root of 2 product of ket m0 plus ket 0n, and using this state we can reach up to the Heisenberg limit. Thus, the noon state protocol is also referred as super sensitive as well as super resolving. Although there are several protocols exist for creating noon states, but in practice they are difficult to implement efficiently for large number of photons. Our attempt to study the squeezing assisted interferometers by using two-channel detection. We proposed two-channel detection, which is a generalized version of a single intensity detection as well as intensity difference detection method. Here, for a squeezing enhanced linear interferometer, we theoretically investigate the possibility to broaden the phase range of subshort noise sensitivity. We saw that this goal can be achieved by implementing detection in both output ports with the optimal combination of the detector outputs. With this modification, the interferometer has the phase sensitivity independent of the interferometer operation point and similar to the standard dark port regime, which is not affected by the laser technical noise, provided that each detector is preceded by a phase sensitive amplifier. This sensitivity could also be tolerant to the detection loss. So the setup is, we consider two inputs. First one is the squeezer, and second one is like coherent state. So these two signals are mixed by beam splitter BS1, and inside that, after traversal from BS1, we have two phases, pi by 2 as well as minus pi by 2. And here we are considering the loss inside the interferometer mimicking by the fictitious beam splitter having transmittivity mu, and the Magenta interferometer with input degenerate optical parameter amplifiers DOPA 1, the squeezer, and two output ones, DOPA 2 and DOPA 3, are acting as to enhance the signal at measurement stage. And here in the measurement stage also, we are considering the loss at two output ports by using the fictitious beam splitters having transmittivity eta and eta. So as we have discussed, there are different limits in the measurement stage. First one is quantum projection noise limit for a two-level emitter. Suppose we prepare initial state in the ground state ket G. Its wave function at the time t is given by ket psi, which is equal to cos omega t upon 2 ket G minus I sine omega t by 2 ket E. The probability of emitter is in the excited state E is associated with the observable P, which projects ket psi t onto E. The measurement results to the expectation value of operator P, which is equal to sine 2 omega t by 2. The optimal measurement point is located at the maximum slope spot, which is equal to half, that is the pi pulse. However, the quantum mechanics imposes a variance in the measurement, which is the product of expectation value of operator P and 1 minus expectation value of operator P. E. The maximum uncertainty also occurs at expectation value of PE equal to half, where while del PE square is minimized at expectation value of PE equal to 0 or 1. The similar result holds for the system composed of NE independent emitters. The measurement signal is proportional to product of NE and expectation value of PE, while the QPN is square root of NE expectation value of PE product of 1 minus expectation value of PE, resulting 1 upon square root of NE with expectation value of P equal to half. This QPN limit has proven in experiment, and the stability of single and clocks has already hit on the QPN limit. Second one is, as we have discussed, short noise limit. In photon detection, the incident light having frequency omega L, power is P equal to IA, with the light beam's intensity I and area A. The photo detector converts the optical signal into the current signal I0 equal to Z E eta product of P upon S slash omega L, with the gain G and the quantum efficiency eta. The noise in photo detector fluctuates the current around I0. That is, IT is equal to I0 plus delta IT with expectation value of or average value of delta IT equal to 0. The root mean square noise current consists of two main parts. First one is short noise, which is given by Schottky formula, and the second one is thermal noise. In detail, we are not going to discuss here. Next one is quantum noise limit. While the short noise limit defines the best possible sensitivity in a perfect case where eta is equal to 1, the quantum noise limit gives the achievable sensitivity for a given experiment with a total quantum efficiency eta total along the optical path, including detector efficiency. Last one is, which is a fundamental limit, that is known as Heisenberg limit. We have discussed earlier. So now we will discuss about the basics of quantum optical measurements. There are many techniques to perform the measurements. For example, we are focused here single mode idealized measurements. For example, homodyne, balanced heterodyne, unbalanced heterodyne, single photon threshold, photon number parity, and photon number resolving detections. A schematic representation of homodyne detection of a state rho is given here. The dashed red line represents a balanced beam splitter. LO stands for local oscillator, that is a strong coherent state. The blue circles are photodiode detectors. Changing the phase phi of the local oscillator allows one to measure the rotated quadratures. So in this way, we can perform the homodyne detection for a state rho. Homodyne detection is a Gaussian measurement by mixing the state to be measured on balanced beam splitter with a strongly excited coherent state, the local oscillator. The intensities are both.
Can I interrupt you?
Yes.
Yeah, there is a question in the chat box.
Okay.
Is quantum projection noise limit valid for both coherent or squeezed light?
Yes, that may occur because squeezed light is a non-classical light, and in that case we are considering the quantum phenomenon. Okay, and coherent state is lying at the boundary of classical as well as non-classical state. So if we are considering the quantum case, then it may be valid for these two cases. So coherent as well as squeezed light. I think this is okay.
Yeah, please go ahead.
Thank you. So for homodyne detection, the POVM elements with phase phi can be defined in terms of this operator, where ket x dependent on phi is the eigenstate of the rotated quadrature operator x phi equal to cos phi q plus sin phi p corresponding to the eigenvalue. Next, we can consider balanced heterodyne detection, which corresponds to a joint noisy measurement of quadratures q and p. This is a Gaussian measurement which yields two real outcomes corresponding to the real and imaginary parts of alpha. POVM elements of balanced heterodyne detection are given by this operator. And in the case of unbalanced heterodyne detection with unbalancing parameter psi equal to r e power I phi, that is and using local oscillator, the blue circles are photodiode detectors. The Q and P measurements are each performed on the balanced homodyne detection. There are examples of non-Gaussian measurements. Any Gaussian measurement can be implemented by Gaussian unitary operators, and heterodyne detection only, since it can be implemented by Gaussian unitary operations and homodyne detection only. There are three non-Gaussian measurements also, each giving more information about the photon number of the measurement state. First one is single photon threshold, or simply threshold detection, for which the POVM elements are written in terms of these relations. This binary measurement only distinguishes the vacuum state from the other states. Second one is parity measurement, whose POVM elements are given in terms of these two operators. This is a binary measurement of the parity operator expressed in terms of -1 power a dagger a, yielding, as its name indicates, the parity of number of photons on the measurement state. Third one is photon number resolving detection, whose POVM elements are given in terms of cation broaden. Here, in our case, we are proposing theoretically a measurement two-channel detection scheme, which is generalized for version of direct detection scheme. We are considering optimal combination of two output signals. The best result can be obtained by combining both outputs with some optimized weight factor, which we denote here k equal to plus minus 1. Our operator is O, which is defined in terms of n minus plus k, n plus, taking into account n plus is independent of phi. The phase measurement, we have error propagation formula like this. Therefore, the value of k that minimizes square of expectation value of delta n k provides also the best phase sensitivity. Optimal value of k and the corresponding value of delta phi are k of, which is equal to cos phi, and this optimal strategy gives us a completely flat value of delta phi. At the same time, it creates the vicious circle. The factor k depends on phi, which itself is the result of measurement. Therefore, consider the suboptimal strategy, which uses the value of optimal value of k, that is k sub r, which is equal to cos phi a priori. Okay, phi APR is a priori mean value of phi. In this case, square of delta phi is equal to square of delta phi minimum plus k product of square of cos phi minus cos phi APR divided by sine square phi. Okay. So in order to obtain good phase sensitivity, delta phi should be much less than 1. The deviation of phi APR from the real phi also has to be small. That is, delta phi APR must be much less than 1. With such a mild limitation, we can write square of delta phi equal to square of delta phi minimum plus k product of square of delta phi APR. Therefore, modest a priori knowledge of parameter phi corresponding to delta phi APR is approximately less than or equal to square root of e power minus 2r1 plus epsilon square upon a plus square epsilon square, which is independent of n and therefore could be much larger than, for example, of Sartmeyer's limit. It allows us to obtain a sensitivity close to the optimal value, which is delta phi minimum for all values of phi. These are our results of our calculations. Here we plotted ratio of delta phi to delta phi Sartmeyer's limit for three cases: single detector, differential detection, and our optimal combination. You can see that the sensitivity of a Magenta interferometer with squeezed vacuum at one input and parametric amplification of both output signals taking into account the optical losses and the detector's inefficiency. We compared three measurements. First one is measurement of the number of photons at one of the interferometer outputs. Second one is measurement of the difference of photon numbers at both outputs. And third one is optimal combination of the numbers of photons measured at the two outputs. While the first two strategies limit the range of phases where the high sensitivity could be achieved, the third one allows us to beat the Sartmeyer's limit by the same amount for all values of phase phi, assuming some modest a priori information on phi. In particular, this information could be acquired using a preliminary low precision ranging measurement with a broadened range of high phase sensitivity. Squeezing assisted interferometers can improve the performance of many techniques where they have not been used so far. That is, first of all, FTIR spectroscopy, where the phase has to be scanned over ranges exceeding 2 pi. Also, measurements of refractive index used in various fields from aerodynamics to environmental gas sensing are based on the phase shifts in Magenta interferometer and will benefit from broadening its high sensitivity range by using our study. Okay. Our next study is to find out some alternative state to enhance the sensitivity of interferometer by using two-channel detection scheme. Here, again, this is the same setup as we have discussed. Here, we change slightly the operator depicting the two-channel detection scheme defined in terms of G5, which is equal to P A3 dagger A3 plus Q A4 dagger A4. In this scheme, the measured data of both output ports are used and they are combined by using optimized values of coefficients P and Q. We can see easily that this TCD scheme converts into the intensity difference scheme for using P equal to minus Q equal to 1 and into single intensity detection scheme using P equal to 1 and Q equal to 0. Our proposed state.
Just one. There are some questions in the chat box.
Yes. What should be the optimal working point for Magenta interferometry for detection of sensitivity? Okay. So as we have discussed here, we have three kind of bounds. First one is short noise limit, second one is quantum noise limit, and third one is which is ultimate bound, that is Heisenberg limit. These three limits limits the sensitivity of our interferometer and optimum working point. To determine such optimality, we use the quantum Fisher information, as well as quantum Fisher information is used to the optimal sensitivity of interferometer, which is independent of any measurement scheme. So by calculating the quantum Fisher information, we can use different detection schemes to find out the ultimate bound on the sensitivity of interferometer by using Kramer-Rao bound. Kramer-Rao bound is delta square phi, which is greater than or equal to 1 upon square root of f, where f is quantum Fisher information. So I think this is okay.
There is one more question before that. What will happen with Homodyne and Heterodyne detection if we use 40 by 60 beam splitter?
Can you repeat again?
What will happen with Homodyne and Heterodyne detection if we use 40-60 beam splitter?
Yes, that is very good question. We are calculating about the beam splitter in spite of 50-50 beam splitter. That analysis will be different, and that will be dependent on the beam splitters transmittivity and as well as reflectivity. Okay, so that will be different analysis.
And there is one raised hand. If there is a quick question, then we could take it now. Vikram, could you? I'm allowing you to unmute. The host, can you please allow him to unmute? Then he could ask the question. Or if you are not able to ask, then please type it in the chat box.
Yes.
We'll take it up. Can he? Is he speaking? Vikram? No, we'll come back to him at the end. There's one more in the chat box by the same person. In case of squeezed light, how the Heisenberg limit will be perfectly valid, as it is somehow shown probably non-classical.
In case yes, in case of squeezed light, how the Heisenberg limit will be perfectly valid, as it is somehow so non-classical. Heisenberg limit is the ultimate bound. Beyond that, we cannot go. There are different states. By using that, we can reach up to the Heisenberg limit, but we cannot go beyond that limit, Heisenberg limit. So you have many options. We have many protocols, or you may try different protocols to reach up to Heisenberg limit. Okay. Squeeze light is an example of non-classical light. So using that and other things also inside interferometer, as well as at measurement stage, you can reach up to Heisenberg limit, but beyond that we cannot go. Okay. And one example is noon state. Using that, you can saturate the Heisenberg limit. But the problem is, problem in noon state is its generation. Okay, for large number of photons. Is it fine,
Yeah.
Chandramani?
Okay, she says.
Okay. Okay, thank you. So our attempt to find out to enhance the sensitivity of our interferometer by using two-channel detection as well as a new state, which is superposition of Schrodinger cat state and Fock state. In this, we are studying here only single parameter case. In that case, we calculated different cases, and here we studied that variation in phase sensitivity with mod A and theta A. Phase sensitivity in terms of mod A and theta A. For values of mod A approximately equal to 1, we get better phase sensitivity, that is maximum phase sensitivity is shown by dark blue region for theta A equal to 3 pi by 4. Other parameters are mentioned here. Again, we studied the variation of phase sensitivity with theta, and we can see here that phase sensitivity can be is varying is dependent on different values of theta A as well as phi, theta B, theta alpha, theta B, n0, mod beta square, and we can see different cases for the enhancement of sensitivity. Comparison of 3 cases when coherent state as well as SEFS state, which we proposed here, vacuum state and SCFS, and coherent state plus squeezed vacuum state. We can see here that we also considered here, we also fixed here the energies or number of photons equal in all 3 cases. We can see here that the combination of coherent state and SCFS is going beyond combination with combination of vacuum plus SCFS. So the combination of input states having coherent state as well as SCFS may work better in some cases. Colorful areas show the corresponding values of mod beta square and phi for which phase sensitivity beats the short noise limit. Color bar shows the ratio of delta phi with short noise limit. Here color corresponding to value 1 shows that phase sensitivity is equal to the short noise limit, and colorless area indicates the phase sensitivity above the short noise limit. So these are different studies under different cases. We can see here the effect of N on phase sensitivity in the case of SCFS. We can see here the value for N equal to 3 as well as N equal to 0. We have better sensitivity as compared to other cases. The effect of N on phase sensitivity for mod alpha square equal to 10 can be seen here. This case is depicting the better sensitivity in our case, which is the combination of coherent state as well as SCFS. The proposal for generation of our proposed state is given here in a building block diagram. A schematic diagram for generating SCVS. Here VS1 and VS2. Here SCVS helps for superposition of Schrodinger cat state with vacuum state. So in this scheme, using this scheme, we tried to generate the state having only n equal to 0, and for higher number of photons we can try this scheme also with some rigorous analysis. So at input of BS1 we mix the single photon with vacuum, and at our using BS2 we mix again vacuum state with the output of first beam splitter BS1, and at one of the output port we apply cross curve media of and output of CKM1 we mix the G signal of BS2 and I signal of CKM1, and output of CKM2 which is K is displayed with minus I alpha, and subsequently we apply phase shifter on this, and we apply von Neumann measurement on the modes J, L, D, and in result we find out the SCVS as at output port of the this block diagram. Okay, these studies have been done with my students, Mr. Devendra Kumar Mishra, Dheeraj, Gaurav, Priyanka, and these two students are new, and these two students are also working on these two projects. So collaborators are Maria Chekhova, Farid Khalili, Stefan, and I have learned a lot about the quantum interferometry with Wang Li and my former postdoc supervisor, Professor Jonathan Dowling, who is no more here, late Professor Hari Prakash of Allahabad University. Okay, thank you very much. So,
thank you very much for this very nice exposition. Now it's time for questions. So participants, you can raise your hands if you have any questions. Maybe Vikram, are you there? If you would like to ask a question now. I think
Vikram.
Left probably.
Okay.
He was raising his hand in the middle. He's not there. Yeah. So he's not there. Yeah, I have a question. Maybe
Okay.
I can ask a question. So you are using squeezing assisted interference, right?
Yes. Yes.
Why is it helpful? I mean, why squeezing is helpful here?
Yes. So that is very good question, and this is very broad question because in interferometry we have 3 steps. So state, we are trying to prepare different states. Inside the interferometer we have some we can modify as we wish, and third stage is which is measurement stage. So our task is to find out some particular states to be used in input port of the interferometer, and after injecting such states at input of the interferometer, that will evolve inside the interferometer, and output port we have to apply the measurement techniques. So squeezing have applications in different areas, as we are well aware, and squeezing have been used in detecting gravitational wave detection, but there are as a first proposal, squeezed vacuum state and coherent state have been successfully used for enhancement of sensitivity of interferometer. Problem is the losses inside the interferometer as well as losses at output of the interferometer, which is measurement stage. To cope with these difficulties, we are trying to use, we can apply different states to study how the sensitivity can be improved in different protocols. Okay.
Okay, thank you. Any more questions? I don't see any.
Okay.
Probably everybody is hungry.
Yes, yes. So everyone is trying to do lunch. Okay.
Yeah, go for lunch.
Especially students, you know.
Yes, yes.
Hostel timings are like that.
So, Poonam, thank you for we have taken your thanks. Devendra, nice talk.
Thank you. So, thank you very much to all of you. So, may I skip?
So we can close the session and go for lunch.
Yeah, sure.
Thank you all of you.
Yeah, thank you.